Hello and welcome to the Society of Environmental Toxicology and Chemistry webinar. At this point, I'd like to hand things over to Gary Kletchka, Senior Fellow, Toxicology and Environmental Research and Consulting, Laboratory of the Dow Chemical Company. Gary, the podium's all yours.
Thank you, Colin. I also would like to welcome everyone to today's webinar on the science of assessing POPs and PBTs with a particular focus on persistence. Today's webinar, as you're probably aware, is the second in this series, and during the first webinar, Derek Muir, Michael McLaughlin, and I presented an overview of the findings of the CTAC-Carlson workshop on science-based guidance for the evaluation and identification of PBTs and POPs. It was comments that we received from the audience during the first webinar that indicated a very strong interest in a more detailed understanding of how to assess persistence. So as a result of that, we engaged Bob Bothling, Jason Snape, and Catherine Finner, who will be discussing the findings and recommendations of their particular work group, which specifically addressed the topic of persistence at the Carlson workshop. To formally introduce our speakers, Bob Bothling is a microbiologist with the Exposure Assessment Branch in the Office of Pollution Prevention and Toxics with the U.S. Environmental Protection Agency. His main interests in most of his published work concern the environmental fate data resources and computerized predictive methods for chemical properties and the environmental fate of organic chemicals. Jason Snape is a principal scientist with the research team at AstraZeneca in the United Kingdom, and he manages their environmental foresight program by tracking emerging regulatory and scientific drivers that can improve environmental risk assessment. He also chaired the ESOTOC Persistence Task Force and the REACH Implementation Project 3.3.2, which is an endpoint working group on degradation. And then finally, Catherine Finner is a senior scientist and research group leader in the Exposure Modeling Group with the Department of Environmental Chemistry at the Swiss Federal Institute of Aquatic Science and Technology in Switzerland. Her key contributions to the study of POPs and PBTs focus on structurally closely related transformation products which may exhibit similar toxicity and persistence as the parent compounds. All right. Some of the information that you're going to hear today is based on a paper that was published by Bob Bothling and his co-authors. It was published in the CTAC Journal, the Integrated Environmental Assessment and Management. And in addition to today's presenters, the other authors on the paper include Phil Howard, Mick Whelan, and Torben Madsen. If you haven't had a chance to read the paper, I'd highly recommend it as a resource for current understanding of the state of the science. It's also important to note that persistence is a very complex property and has been the subject of numerous conferences over the past 15 years. And this slide highlights a number of the important workshops and publications related to persistence. Among them are quite a number of CTAC workshops beginning in 1994, but primarily in 96 with the Port Sunlight workshop on biodegradation kinetics, followed in 1998 with our first Carlson workshop on PBTs and POPs, which focused on persistence and long-range transport, and then finally the most recent Carlson workshop that we had. But ESOTOC, which is the European Center for Toxicology and Ecotoxicology of Chemicals, has also been very active in stimulating discussion on the assessment of persistence and has held a number of workshops on this topic and has published a number of technical reports. These are also excellent resources for understanding the current state of the science. So during this morning's webinar, you're going to be hearing again from Bob and Jason and Catherine in that order on a series of topics. Bob is going to speak first on topics that he's entitled Deconstructing Persistence, and then Jason will then speak to intelligent approaches for assessing persistence, and then finally Catherine's going to address the issues related to interpreting persistence data. And then following these three formal presentations, we're going to have a brief question and answer session that will provide you with an opportunity to clarify any points. And then afterwards, we'll be covering a series of case studies to illustrate selected points related to persistence assessment of those compounds, and then we'll have another question and answer after that. So with that, I'm going to turn it over to Bob Bothling for the first presentation.
Hello, class. Good morning. I'm glad to be here, and I hope you are also. Well, This first slide of mine just highlights of what I'm going to talk about, what persistence is, why it's important, criteria for persistence, an overview of processes. I'm going to talk about partitioning for a while, and use of non-test data, which you probably know better as structure-activity relationships, or SARs. Now, each one of these, of course, is a whole seminar unto it. So I'm not going to cover each one in much depth at all. In fact, it's going to be quite superficial. Well, what is persistence? You know, there are many definitions, and too many to describe in this presentation, but I just put a couple of these on the slide here, and really one of my favorites is the first one, which is, so I'll just read that to you. I won't read both of these to you. The tendency of a chemical to remain in the environment without transformation or breakdown into another chemical form. And this is this second sentence here is the part I like the best. The reason I like this is it's quite succinct and really gets to the heart of the issue. Persistence refers to the length of time a chemical is expected to reside in the environment and be available for exposure. An interesting sidelight on that is it's from a website which I found by Googling called thriftyfun.com, and it has such interesting things in it as what breed is my dog and my frugal life, 10 reasons to embrace the frugal lifestyle. So you can find interesting things. Who would have ever expected to find information on persistence in that kind of place? But there it is, and it's a good definition. The second one is from an EPA tool called the PBT Profiler. It adds a little bit to the first one, and particularly the last sentence on the slide, which mentions the specific environmental media that are most relevant. Well, this slide is intended to show in a very graphic way why persistence is important. Now, there are many assumptions that go into making this, and the details are not really what's important here. What I'm trying to show is the effect of varying biodegradability of a chemical on the mass of the chemical in soil. And so you have various assumptions about release rates and so forth, but the main message is that if you have a chemical that's not biodegradable, it accumulates in the environment and stays there. If you, even with the half-life of 100 days is really, once input to the environment ceases, the chemical does go away, but it still takes quite a long time. Half-lives have to be relatively short for the chemical to disappear quickly when input to the environment ceases. The bottom line is shown in the yellow text box here. Substances that don't degrade or degrade slowly remain available to potentially exert toxic effects, bioaccumulate, or be transported to other regions. This slide summarizes criteria for persistence under regulatory and international frameworks. It's a fact that persistence is still expressed in a regulatory context as single medium half-lives, and in particular as point estimates. This slide doesn't include all persistence criteria that exist in the world, but some of the more major ones. For example, UNEP, you probably know better, is the Stockholm Convention. There are different values given for air, water, and soil, and some EPA values are in there also. SEPA is Canadian Environmental Protection Act. So the point really is to show there are many different values, and the result of this is that a chemical that might appear to be persistent under one jurisdiction may not be under another. And this makes assessing persistence even more challenging than just the challenges that arise from considering data. There's no one correct value here. It's expected that the criteria should vary because the objectives, history, and constraints of these frameworks vary also. And also in each case, the persistence assessments are formally based on a comparison, as I just said a moment ago, of single media half-lives to the criteria. This may not always be the best measure of a chemical's overall environmental persistence, which is I'll return to later. Above all, persistence is one facet of a chemical's behavior or fate in the environment. And so what I'm going to do now in the next few slides is just expand the notion a little bit. So I'm going to be talking about the environmental fate of chemicals, which is a little bit more general notion than chemicals' persistence. So why evaluate environmental fate? Well, here are some of the reasons. We want to know how a chemical will behave in the environment. And once released, we want to know if the chemical will go to air, water, soil, sediment, or some combination of those media. Of course, persistence here shown as an aspect of environmental fate. We want to know how long a chemical will persist in the environment, and how might humans in the environment be exposed to the chemical. It's important to understand in assessing persistence that it's not straightforward. Persistence can't be directly measured. It's also not an intrinsic substance property. It can only be inferred, and the types of evidence that we consider are a lack of observed degradation in laboratory or field studies, test data in other words, but also predictions from models, SARs, which I referred to just a couple slides back, in combination with the continued presence of a substance in the environment. That is, of course, where monitoring data exists. So the message here is that all these things need to be considered, and really it's important to understand that simply detecting a chemical in the environment by itself is not evidence of persistence. Now, moving over to the right side of this slide, what I've tried to do here is summarize all the different factors that go into determining a chemical's apparent persistence in the environment. Some of these we're not going to be discussing in this webinar. For example, use and release pattern and tonnage and things like that. Primarily, we're going to be looking at the material in the text boxes, chemical structure and substance properties, transformation processes, and also transport processes. And so the next few slides I have will address those subjects. Well, this slide summarizes physical, chemical, substance properties. Now, this is in addition to the chemical structure, which I didn't put in the slide. There are two types of properties to consider here. First, are common pure substance properties like melting and boiling point. I won't try to read every line of the slide here, but secondly, partitioning and other properties. And this is including properties which are, for example, octanol water partition coefficient, which everyone's probably familiar with. All the partition coefficients, in other words, would be included in this category, Henry's law and so forth. Also, dissociation constants, pKa and pKb. I see from the slide the A and the B should have been subscripted. This list isn't exhaustive, but summarizes most of the things we need to consider. Degradation processes. Well, the way the slide is organized is mostly by media. In the atmosphere, we consider photooxidation by hydroxyl radicals, ozone, and nitrate radicals. Those are the three primary oxidants. There is also direct photolysis occurring, which can only occur when a substance absorbs light in the visible range. In water, soil, and sediment, hydrolysis and biodegradation are usually the most important processes. Direct and indirect photolysis can also occur and be important for some types of chemicals. Chemical reactivity, for example, with the oxidants and reductants in the environment, and as the next big processes dominate, of course, in reducing environments. In waste treatment, any of these things can be important. It really depends on the situation. We can say, to generalize, light exposure is typically less important for that type of environment. Environmental transport. Well, this is just as important in determining environmental fate as is persistence. And this is referring primarily to physical processes. These include, for example, advection, which is movement of air or water, volatilization, absorption, and simple dilution. Physical processes impact the chemical's concentration in a given phase and its distribution among the phases. It can also result in long-range transport, for example, to the Arctic for certain substances under certain conditions. And also bioaccumulation can be thought of as an environmental transport process because it results in distribution of a substance. Well, when we put all this together in assessing persistence, we have this kind of picture. Now, this is a somewhat confusing slide, and I guess that's by design. It's designed to show how complex the process can be. This shows interaction among media and all the different physical processes that can move chemicals from one place to another. And it's too much really to try to go over in great detail. So you'll be able to spend more time on that when you download the slide deck. I'm going to turn for the next two slides to SARs and just say a little bit more about this. Now, again, SARs are structure-activity relationships. You may know that by the more familiar acronym QSAR, which stands for Quantitative Structure-Activity Relationships. This SAR generalizes this notion to include all of the in silico methods, whether they're quantitative or not, for calculating or in other words, estimating chemical properties or degradation processes from some other parameter. Why would we use such things? Well, we find that oftentimes empirical data are not available for some chemicals, particularly in chemical screening. We need to understand the limitations of SARs need to be understood, and in particular the applicability domain. In other words, which chemicals or chemical classes a given relationships are applicable to. This is not always easy. Another important point, really more important than what I just said, is to try to use reliable data from empirical studies. This should carry more weight than data from SAR. Or from predictive tools or estimates in any assessment activity. So the next couple of slides, I'm going to give you some examples to try to illustrate what SARs are and how they work. So the first one, I have 3 slides on this topic, and the first is an example from the KOW-WIN program. This program calculates octanol water partition coefficients. It uses a fragment-based method which basically sums up the fragments from the fragment library for the method and correction factors and multiplies the coefficients of those fragments times the number of instances of the given fragment in the molecule and comes up with the estimate of the property, in this case log KOW. So this just shows you, this is for the chemical L1L isoleucyl L-proline, and it sums up all the fragments that it found in that molecule and makes a calculation in the way I just said to come up with an estimate of, for this Witter ionic material, of minus 1.6 for the octanol water coefficient. And you can see just by coincidence that it happens to be pretty close to the experimental value, which is up toward the top of the slide there, minus 1.79. Also on the KOW-WIN program, this slide shows a plot of the estimated log KOW versus experimental value, versus the experimental KOW for the validation set that was used during the process of model development. Typically, when you develop a model like this, you use a separate set to develop the relationship and then another set to test it, basically, or validate the relationship. The statistics for both the validation and training sets are shown in the slide just as an added bonus here, but the plot is for the validation data of 10,946 chemicals with pretty good R-squared. And my last slide on SAR, this is example number 2. This is for the Bio-HC-WIN model. This is an EpiSuite. It's the model that predicts hydrocarbon biodegradation half-life for a typical or evaluative, to use Don Mackay's terminology, aquatic environment. The relationship is shown on the left side of the slide. Again, it's just a fragment-based method where you log half-life equals a summation of fragment coefficients times the number of instances of that given fragment summed up over the molecule, and then that's the way you get the half-life. And the plot is copied from a PDF file showing the predicted log half-life versus the recommended, which is to say the measured value for that given training set. And also, in addition, it's a little hard to see, the half-lives, the measured half-lives and the corresponding estimates are broken out by hydrocarbon class in this particular figure. So you have separate symbols for example, the cyclic alkanes and the aromatics. Now, this is one of my favorite slides because it's good. It does a good job of injecting a dose of reality to the assessment process here. What you're seeing here is a distribution of 26 measured half-lives for diethylhexyl phthalate biodegradation in soil and sediment, and there are probably more data now. This is 10 years old. But you see the point is that there's no one value for the soil biodegradation half-life for DEHP. You have all these data to consider, the half-lives varying from 10 values. This is published data. 10 values we found that were in the 0 to 50-day range for half-life, and one value that was above 600 days. So if you're an assessor, the question is how do you weigh all this information to come up with a value for your persistence assessment? Now, remember what I said about the criteria or half-life, the half-life values that are used in the regulatory frameworks like Stockholm. They're specific values like 3 months, 6 months, and so forth. This is the reality of environmental data. What do you do with this? Catherine is going to talk a little bit more about this later, and I think I don't want to steal too much from her, but I think she'll show that you can fit a curve to the data if you have enough data like this and manipulate it in various ways to come up with a number. My last couple of slides here, I want to turn to the importance of determining the most relevant medium or compartment. The environment as a whole is a set of interconnected media, air, water, soil, and sediment. For any individual medium like soil, persistence is, of course, a function of reactivity and that substance's tendency to remain in or partition out of that medium. Those are the topics that I've just been talking about prior to the SAR slides. It's very important to identify media or compartments that are most relevant for a given chemical. Focusing on the wrong one can lead to erroneous conclusions. And to give an example or illustrate that a little bit more clearly, a substance might have a long half-life in one medium but partitioned to another where its half-life is very different. So, for example, imagine you have a very volatile chemical which is released to water. It, for example, might have a very, just take a hypothetical example. If that chemical has a very long biodegradation half-life, you might conclude just looking at its release to water that it would be a persistent chemical. However, if the chemical is very volatile, it would quickly leave water, go into the air, and in the air, typically, oxidation of chemicals persistence of chemicals is typally lower in air because of the powerful oxidants that exist there. So we might reach a completely different conclusion regarding the overall persistence in the environment. It's easy to be misled by individual media. Don't consider the environment as a whole. And the last slide in my part of this expands on that a little bit in talking about multimedia persistence, and in particular multimedia models, which are a convenient way to take all these factors into account simultaneously. Multimedia mass balance models are also referred to as Mackay-type models, are often used for this purpose. These models also can calculate a parameter called the overall persistence, or POV, which is a quantitative measure of multimedia persistence. And in fact, POV as a specific parameter is only calculated by such models. They're typically used at the screening level and can identify the types of chemicals that would be types of data, that would be most useful, and therefore testing if additional testing is needed. Jason will talk more about testing, but for example, if it may come from the model that soil is the most important compartment for a given chemical, and so then testing might want to focus on that. In the confirmatory phase of assessment, the models can also be useful in evaluating the relative importance of half-lives from different environmental compartments. The reason that's important is it's important in determining where the weight of evidence lies when we're conducting a persistence assessment, and we have to consider all kinds of data for all compartments. We want to have some idea of which ones are the most important for a given chemical. The multimedia models can help in that regard. So that concludes my part of this. I'm not sure how long it took, but I guess Jason can take over now. Jason?
Thank you, Bob. I'm going to spend the next 20 minutes giving an overview of the strengths and weaknesses of the existing standard biodegradation tests with respect to kind of assessing environmental persistence, and then just talk a little bit about some of the progress with regard to environmental persistence assessment, and then try and have a quick look to see how I can actually bring some of these studies together with other evidence of degradation and modeling in an intelligent fashion to actually conclude on the persistence endpoint. I think that most people are going to be aware of the OECD kind of biodegradation testing paradigm, where we've got the three tiers of biodegradation. So we've got the ready biodegradation tests, the inherent tests, and the simulation test. This has been in place, I think, basically now for about 30 years, and there's been quite a big shift going away from kind of tests to identify kind of chemicals that can undergo rapid ultimate degradation in the environment to actually trying to understand what chemicals are likely to be persistent in the environment. And obviously this hierarchy of tests that we have some kind of inherent kind of properties that actually go from quite simple studies that are extremely kind of stringent and very, very cost effective and have low degradative power to quite sophisticated simulation type studies that can quite often be difficult to interpret in some cases, and I know later on I'll try and draw out some of those issues, and kind of Catherine will also build on some of the interpretation issues with this data. Finally, there's also been quite a marked increase in kind of the amount of environmental monitoring and biomonitoring that attempts to identify chemicals of concern based on the presence in biological or environmental matrices. And with the ongoing advances in environmental and analytical chemistry, I think these types of studies are only set to increase, but the big challenge that we've got is always about linking presence with risk and adverse effect, and trying to draw kind of similarities between some of our lab and our field operations and observations. In addition to the test-based approaches for assessing degradation and persistence, there are a number of predictive tools and models, and Bob's given a little bit of an insight into that already. Some of the QSBRs that can predict the likelihood that a chemical would degrade or whether or not they're going to be readily biodegradable. You've got tools that can predict the pathways for biodegradation, so we've got things like Catabol and the University of Minnesota pathway prediction software that I know Catherine does a lot of work with. We've got models to help identify the compartments of concern, as mentioned by Bob, so things like the Mackay level models. But we've also got quite sophisticated models to establish predicted environmental concentrations, be them for generic environments or be them for quite bespoke, specific environments. And then in addition to kind of the standard kind of testing paradigm of the ready, the inherent and the simulation tests, Rich has also identified some modified tests, but also some enhanced tests. So it's how might we kind of start using some of these studies, but also some of the newer OECD guidelines, things like the OECD 314 test system. I'll talk a little bit about some of those moving forwards. As I identified earlier on, the first tier of biodegradation tests and the starting point for almost all the regulatory frameworks is the ready biodegradation test. And as most of us will be aware, these tests were originally designed to screen out or identify chemicals that undergo rapid and ultimate degradation, mineralization in the environment through their normal routine usage. So it's to get out the chemicals that represent no environmental concern. So as such, they're actually kind of very, very stringent, and they actually have a high false negative rate and that can be attributed to kind of the low level of biomass we use in the study, the relatively high test compound concentration, the fact that the test compound is there as a sole carbon source, and that the pass criteria are based solely around the mineralization endpoint. This does create a little bit of a problem for us because they weren't designed to identify potentially persistent chemicals. So if the substance actually passes this test, you can actually be confident that it's unlikely to persist in the environment. But if you actually fail the test following the OECD pass criteria, it actually doesn't really tell you that much about the chemical's potential to persist in the environment or its ability to degrade once it's released into the environment. I think we also have to consider that the READY tests represent a series or a suite of 7 different tests, and they actually really aren't truly standardized. We've got things like different preconditioning regimes, different test apparatus. We've got the closed bottle test having slightly different mineral media. We have different endpoints. We can use different sources of inoculum or composites of inoculum. And basically, as a result of that kind of variation in terms of the lack of standardization we have, we can actually have a high potential for conflicting and variable results. And when we're faced with those varying results, normally we have to give kind of most weight actually to the positive results following kind of the OECD criteria, and basically trying to determine whether or not the negative results or the positive results are actually well documented, whether or not the test guideline criteria are fulfilled, and whether or not the inoculum is being pre-exposed or not to the test compound. So basically, if you can bring that and actually be able to draw a conclusion and be confident that actually if you've got a positive and it's not been from an adapted source, OECD clearly state that that can outweigh the negative results. If you think about just looking at some of the variables, again, across all 7 of the READY tests, so we've got the 301 series here, but we've also got the 310 tests of the CO2 headspace test. Quite clearly, they're standardized in terms of the test duration of 28 days. We've got the different endpoints here, some being direct measures of mineralization, such as carbon dioxide evolution, but others being kind of indirect measures. But we've got quite big variation when we start to think in terms of the chemical concentration, where we can go from concentrations of 2 milligrams per litre up to 100 milligrams per litre, but also orders of magnitude of difference in terms of the inoculum kind of concentration from 0.5% weight to weight secondary effluent to 0.05% by volume. And if you think just about conducting 2 different tests with the same biomass level, so in this case, if we think about the STERM, and we conduct it at 30 milligrams per litre, and if we conduct the CO2 headspace test, again at 30 milligrams per litre activated sludge, the 310 test, the CO2 headspace test, will actually only have 3 milligrams of biomass because it's a 100 milliliter study. But if you actually conducted the STERM test at the volume of 3 litres, the maximum volume, you would have 90 milligrams of biomass in the test, so a 30-fold difference between just 2 of these READY tests, so hence you're going to see very, very different results. We think about the data that we will see from a READY test. Our ideal is on the left-hand side, so we'll actually see a positive result. Here's some data from the STERM test where the 60% pass criteria has been reached in the 10-day window, and we can get rapid conclusion in terms of the default rate constants and get a screening assignment of non-persistence. But this graph is atypical of actually many of the chemicals that I see and work with on a day-to-day basis. Quite often we get extended lag periods that can be attributed to toxicity, the high chemical levels that we got present, the low biomass levels, or the relative insensitivity of the endpoint. We can get very high levels of variation between replicates. We can get non-sigmoidal curves, either biphasic or multiphasic. And here I've just provided 2 curves on the right-hand image, which just shows the degradation of some halogenated aliphatics, where we've got one compound, again showing a typical degradation kind of curve, but we've got another compound actually that's biphasic, and it's only actually within the 2nd phase of the study and exceeding the test beyond the 28-day period do we actually see extensive degradation. So we get a lot of variation in terms of the results we actually see and the shapes of the curves we see that make it difficult to interpret. But we also get a high number of fails. in many cases, the chemicals fail to actually hit that 60% pass criteria. And that can be attributed to a number of reasons, most of which are described within this slide. But actually only one of them is related to the fact that the chemical is actually not persistent. And we also got to remember that the test actually measures ultimate degradation, and quite often you will see partial mineralization in the region of 20 to 60%, but you can get extensive primary degradation that's being missed. We've got other issues about kind of the chemical being introduced at high levels that are toxic to the biomass. We've got having low levels of biomass actually going in to the test, which can actually result in the absence of competent degraders. But we also have things around kind of bioavailability issues and mass transfer issues when we're testing poorly soluble material. And actually to overcome a couple of these kind of issues resulted with the high failure rate, particularly the toxic level at which the chemical's being introduced and some of the bioavailability issues. REACH has actually identified two simple modifications. One is actually to test at the low substance concentration level to actually negate the toxic effect, and actually to do this while fixing the biomass level and not actually lowering the biomass level to the same ratio. And the second one is really kind of formalizing the ISO guidance for enhancing the bioavailability of the test material. So actually formalizing the use of solvents, emulsifiers and carriers for poorly water-soluble substances. So here's on the bottom right image is some data taken from Case Van Ginkel, which is just showing the degradation of a particular kind of poorly soluble material, where with direct addition, which is kind of the closed square, we see no degradation within the biodegradation test. But actually if you're using silica gel, or you're using either some lignings or humic material, then we can actually enhance the rates of degradation. So it's enhancing bioavailability within the test. In terms of the test itself and the competent degraders, we have to see the READY test as a bit of a lottery. And the most common reason probably for failing the test is actually not getting a competent member of the microbial community actually into the test and maintaining its biodiversity. Basically, it just comes down to chance of having that organism, and but it's a lottery that you're actually running on which quite significant regulatory decisions are made. So here we've got an environmental kind of reservoir at the top with a competent degrader in red. If you move into quite large vessels, you have a high chance of actually capturing this competent degrader. If you move to small vessels, you've got a lower chance through probability of getting that competent degrader and a higher fail rate actually for that compound. So the test vessel size and geometry is actually important. And there's a number of ways in which you can get around this. It could be increasing the vessel size, you could increase the cell density at which you test, or you could pre-expose or adapt the inoculum prior to testing. And to try and pick up on some of those issues, REACH has actually highlighted some enhanced procedures for use in kind of persistence assessments. And some of those are quite simple schemes that actually don't really alter the inherent nature of the test or the inoculum. So these include increasing the test duration beyond 28 days, or actually working in larger test vessels or at higher cell densities or a range of cell densities. And I'll spend a little bit of time looking at some of those examples later on. We've got two other kind of enhancements that have also been identified, which actually allow for low-level laboratory-based operation. So it includes the semi-continuous operation, or the fill and draw approach to testing with environmental waters. And that work's been described in the past by Lars Terang and Niels Nyholm and forms the annex to the OECD 309 guideline. The final enhancement down the bottom here is just basically having a simple kind of two-phase enrichment where you run a READY test, and then you can take the inoculum from that test, you wash it, and you run a second READY test in series to establish whether or not you can reduce the lag periods. So in terms of two examples really around increased vessel size and increased density, we got some of the work here from Fleming Ingerslev back in 2000, working in the Niels Nyholm group, that actually shows the importance of vessel size when you have mixed microbial communities. In these studies, we've actually got a cell density that's actually fixed, but we've got a different size of volume there, which actually enhances the biodiversity or the amount of different microbial capabilities you bring in at bigger bottles. So here we're seeing at the higher bottles on the right-hand side of the first image, where you've got the highest levels of kind of volume and the highest level of biodiversity, actually resulting in shorter lag periods and more extensive degradation. As you actually drop the volume down, particularly less than kind of 10 milliliters, you're actually having an increased chance of false negatives for this kind of study. And on the right-hand side, this image just shows the lag duration in terms of kind of the test volume, and basically we're seeing much shorter kind of lag phases with increased kind of test volume. So quite clearly the vessel size has a marked impact on the degradation we see. Another approach is actually to fix the volume and actually change the cell density, and through that route actually bring greater biodiversity in. And the concept, or the proof of concept for these studies, was established by Gerald Tuon back in 1995, and that work's being built on by Andy Goodhead, Russell Davenport and Tim Martin and myself. And here we're not looking at a standard kind of biodegradation curve. We're actually just looking at the cell counts per mil and the probability of seeing ready biodegradation, so hitting this 60% pass criteria. Each line on the curve actually represents a different inoculum source, and the red dash line going up is the maximum level of biomass you will actually see in a ready biodegradation test. And quite clearly for these two different chemicals here, chemical Y on the right-hand side, no matter what inoculum source we actually used, we failed the ready test at this ready test concentration. But actually, if you increase the biomass concentration by 10, 100, or even 1,000 orders of magnitude, the probability of hitting that 60% pass criteria did actually eventually reach 1. For chemical Y, that actually happened much earlier, so it's a lot less recalcitrant against the inoculums we actually tested. The second tier of biodegradation is obviously the inherent kind of test. We've got 3 tests at this level, kind of the SCAS, the Zarn-Wellens, and the MITI test. And basically these were designed to establish the potential for a chemical to biodegrade. And whilst they're not necessarily favoured by all parties for the use in persistence assessment because they rely on sewage treatment inocula, you can apply specific criteria both to the Zarn-Wellens and the MITI test to actually conclude on environmental persistence. So if you get degradation within a week with a defined lag and log period for the Zarn-Wellens test, it can be concluded to be non-persistent. If you get degradation within 14 days for the MITI study, again you can get evidence of non-persistence and degradation. However, if you fail these studies, so you get less than 20% evidence of degradation within the test, then you've got pretty good evidence and conclusion that your compound might be persistent. And just here again on the bottom graph, we're just showing kind of a range for one particular chemical, looking at the respirometric endpoint, a range of biomass levels going from the sub-ready test level right the way up beyond the levels you'll see in a Zarn-Wellens, actually showing that the probability or the potential and the rate of degradation increases with biomass concentration up to about the levels you'll see within the MITI-2 study. As you actually increase beyond the MITI-2 study, the rates of degradation decrease because of the amount of exogenous material and exogenous carbon you have in the study. In terms of the final tier of testing I'm just going to focus on at the moment is just the simulation tests. And I don't like actually calling them simulations. I prefer to call them higher tiered studies because with the exception of the OECD 303 wastewater treatment simulation, none of them are really simulations. They're just basic batch studies, so just bigger, more complex versions of a ready test. And obviously we've got a significant increase in the cost and time that actually takes to do these studies. And in many cases, they actually don't have validity criteria. The notable exception is the OECD 309. And not only do they lack validity criteria, many of them actually don't have positive reference compounds. So it's difficult to compare data or to understand whether or not the test has performed well or failed. Perhaps the test with the most experience to date is probably the soil biodegradation study in terms of plant protection products. But for a lot of the different kind of general chemicals being tested under REACH, there's an absence of data for many of these studies. And I'm just going to spend a little bit of time just focusing on the 308 study. And really this was a test that was originally designed to determine the fate and metabolism of plant protection products in small ditches near agricultural fields that were exposed kind of via spray drift. But at the moment they're being seen by many as a bit of a river water simulation test, and this in my view is a bit of a misuse of the study. This slide basically just describes the aims of this water sediment transformation study. So it's there to measure kind of transformation rates, to get DT50 rates for the water, for the sediment, for the total system. You're trying to measure levels of mineralization, but also identify and quantify transformation products that are actually formed during the course of the study. This slide shows a typical layout within the laboratories that I have here at Brixham. So in the left-hand image, we can see the test vessel here containing the water and the sediment. It's coupled to a purge and trap system, and we've got a water-sediment ratio of between 3 and 4 water to 1 part sediment, and we run with 2 different sediment types. This slide shows some of the typical data that we actually see from a degradation study conducted with the 308 test. So here we will see very, very little evidence of CO2 being produced with time. We see rapid dissipation with the pink curve actually from the water phase, and we're actually seeing increasing levels both in the sediment, either extractable or non-extractable, over time with the yellow and blue lines. And the information on the right just actually brings together data from 36 human medicines that's been compiled by John Erickson, taking data from Pfizer, AstraZeneca, Novartis, and GSK. It's actually shown that it's quite often we actually can't derive a DT50 for sediment or for the total system because these non-extractable and extractable residues are increasing at time. We're actually showing that most of the radioactivity is associated with sediment at day 100. And typically about 44% of this is not extractable, so we don't know if it's parent or transformation product. And we're seeing rapid dissipation from the water phase, and I know Catherine's going to talk about this a little bit later. And the final kind of test that's actually coming to the fore at the moment is the OECD 314 test. And basically, this is trying to follow the fate and behavior of a chemical that's for a down-the-drain chemical, basically. And I think this can provide quite valuable data for both exposure and persistency assessments. So we've got things to assess in sewer removal in activated sludge, so it's an improved Zahn Wellens. It's bringing together primary and ultimate degradation. So we've got some examples taken from, again, John Erickson's work of Pfizer, showing rapid removal of the parent compound, production of metabolites, but also formation of CO2 over quite a short time period. So it's focusing on the hydraulic residence time and the sludge residence time of the activated sludge plant. But we can also assess degradation in the river water environment, both in the mixing zone, below and outfall, but also in the non-mixing zone. Okay, just in the final kind of 2 minutes or so on my slide set, I just want to focus a little bit around kind of some of the intelligent testing strategies. And Gary earlier on identified a number of workshops, task forces, and committee activities that have taken place over the last decade or so, most of which, as he said, coordinated by CTAC and EQUITOC. And nearly all of them have identified intelligent approaches for assessing persistence that kind of maximize the use of existing standard and non-standard data whilst targeting the generation of kind of new, more relevant kind of data where there's an absence of data. So they have a screening and a confirmatory kind of phase. And the core element of most of these tests is they actually start from the same starting points, having evidence of ready degradation and hydrolysis tests. So you can use the ready test in the absence of the 10-day window or evidence of rapid hydrolysis to make a screening assessment of persistence or not. I know within Canada and CEPA, they actually set the pass criteria for their prioritization for the ready test at about 50% mineralization. And again, if you're seeing rapid primary degradation, be it in a ready test or be it in a hydrolysis test, then you can actually need to consider the PBT properties of the degradation product. The second phase in any intelligent testing strategy is probably the most difficult part, and that's actually relying on a weight of evidence. So it's trying to bring together what data we do have, both standard, non-standard, but also predictive in silico work to see if we can conclude on persistence or non-persistence. So it's quite an intricate assessment. So it's trying to say, what do we have? Any marine data? Is there inherent data? Does that inherent data fulfill the rapid degradation criteria, or is there less than 20% degradation? Can we conclude on persistence or not? Do we have any other screening data? Are they enhanced studies or not? Do we have any QSAR predictions or read across from other groups that either provide evidence of persistence or non-persistence? Do we have hydrolysis data, photolysis data, and what pure culture data actually exist? And it's actually how can we bring that together as a weight of evidence and actually decide on whether or not the chemical's persistent. And it has to be using a lot of expert judgment on a case-by-case basis, but paying particular attention to the provenance and the source of the inoculum. If you can't actually make a conclusion at that screening level based on all the existing data, standard or non-standard data, then you have to move towards having kind of a confirmatory study. And that means actually focusing on conducting confirmatory studies on the most appropriate compartment. So this relies on actually bringing together all the knowledge you have about the use and release patterns of the chemical together with the phys-chem properties, and using that within some of the distribution models as advocated by Bob earlier on to actually identify the most relevant compartments of concern. And once you know what the most relevant compartments of concern, be them marine waters, be them estuaries, surface waters, whether or not there's potential for atmospheric kind of transport and deposition to oceanic environments, you have to pick the most appropriate criteria and most appropriate test in which to conduct your study. And then you've actually got to evaluate that simulation data and compare it to some of the persistence criteria that Bob highlighted earlier on. And that's where some of the challenges actually really arises in interpreting some of these simulation or higher tiered data and dealing with multiple kind of degradation endpoints. And that's where Catherine's going to focus on now. So I'll hand over to you, Catherine.
Thanks, Jason. Hello, everybody. So what I'm going to talk about is that besides the different testing methods, there are other issues with interpreting degradation data to assess persistence. And these include, amongst others, whether and how rates from different degradation processes can be combined to yield compartmental half-lives, how transformation products could and whether they actually should be considered in persistence assessment, how to derive compartmental half-lives in cases where you have non-extractable residue formation, whether and how to adjust for environmental factors, and also how to deal with ranges of half-lives or conflicting data. So let's move to the first point. The issue here is that obviously many of the standardized degradability tests attempt to study one process to the exclusion of other processes, whereas in persistence, in POP regulation, always refers to compartmental half-lives, as we've seen. So to then profit from the available process-specific data, we suggest that generally compartmental half-lives can be calculated from the sum of the process-specific rate constants, such as photolysis rates, biotransformation rates, hydrolysis rates, and so on. However, there is one important note of caution that should be made here, and that is that if you do sum up rate constants, it's important to ensure that these rate constants are really compatible. So, for instance, if you sum up biodegradation and hydrolysis rate constants, this should only be done if hydrolysis has really been explicitly excluded from the biodegradation data, for example, by subtracting data from abiotic control experiments. Also, for instance, primary and ultimate biodegradation rates obviously should not be added up. They refer to two different endpoints, as we've heard, where primary biodegradation describes just the transformation of the parent chemical, and ultimate biodegradation really describes the overall mineralization rate, and in that sense also includes parent compound degradation. Now, there are exceptions to the preceding slide's statement that rate constants can be added, and I'll mention two important exceptions in the next 3 slides. The first exception is that transfer to other compartments should not be considered as a loss process, since it is really only transfer of chemical from one compartment to the other. And the most prominent example for this kind of data are water sediment studies that have been carried out or are carried out according to OECD 308 testing guidelines. So in these studies, what you often see reported are disappearance times, so DT50 values, for example, for water. Now, this DT50 value includes degradation in the water, but also transfer from water to sediment. So it doesn't really reflect the persistence or the degradability in water. You can nicely see it on this example here. So if you only look at the water phase, you would derive a DT50 value of about 20 days. But then if you look at the sediment data, you see that this is actually mainly due to transfer into the sediment compartment, which goes up to about 30%. So the only kind of data that, or degradation rate that you can truly derive from this study is degradation in the overall system, which would then have a half-life of about 60 days. Now, if you really wanted to derive a degradation half-life in water, you would have to fit the kind of a two-compartment model that includes degradation in both compartments and also transfer between the compartments to this data to back out the degradation rate in water. The other important exception are cases where non-extractable residues or bound residues are formed. So these are cases where the parent compound is not only transformed to a metabolite that can then be further mineralized, but it is also transformed into non-extractable residues. What are non-extractable residues? For those of you that are not so familiar with this, this is basically a fraction of the original test substance that is not mineralized, but that is also not recovered via exhaustive sequential extraction of the solid matrix. And by this I mean, for example, Soxhlet extraction or supercritical fluid extraction. This is best, the formation of non-extractable residues is best followed with 14C labeled substances, and they would then indicate residual radioactivity in the extracted solids matrix. There are different mechanisms for non-extractable residue formation that are possible and that are discussed in the literature. These include covalent bond formation that is quite well known for aniline type compounds or phenols. It can also be just polymerization of compounds or pure physical intercalation into non-accessible parts of the solid matrix. Now, if you then just look at disappearance of the parent compound and you derive a DT50 value, you're really including both processes, transformation to the metabolite, but also non-extractable residue formation. If you want to truly assess the degradation half-life, you have to back out the transformation rate from the parent to the metabolite out of this data, and this can really only be done by fitting this kind of four-compartment model to the data. This has been done, for example, by the group of Michael Muttis at the University of Osnabrück. He looked at 8 compounds, and for 5 of them he could actually compare DT50 values with DEC-T50 values, and you see the ratios in this column here, and these ratios vary somewhere between 1.5 and 2.5, meaning that the DT50 values might overestimate actual degradation by about a factor of up to 2.5 for these examples. So the issue that is being debated now when it comes to non-extractable residues is whether they can become bioavailable again over time, or for example when encountering different conditions, or whether they're truly non-available. If they were truly non-available, they could be interpreted as degraded, and it would be correct to assess persistence based on DT50 values. Now, the recommendation of the working group on how to derive degradation half-lives in the case of non-extractable residue formation basically was that usually, as a base case, the actual degradation half-life should be calculated and used for persistence assessment, but that there are exceptional cases in which it might be justified to use the DT50 values or the disappearance half-life, and these would be cases where it can really be demonstrated experimentally that covalent bonds with organic material are formed, or where covalent bond formation has been shown for structurally strongly related compounds. Let me jump now to the question of whether or not to adjust for environmental factors. So basically, factors that you could adjust the half-lives for include things such as temperature, pH, humidity, etc. There are different ways of doing this that are discussed in the literature, for example, Q10 rules, which basically indicate a factor by which a half-life would be corrected for a 10-degree change in temperatures, or the Walker equation that has been suggested for correcting humidity. The question really is whether we should adjust half-life to environmental conditions? And the answer to this question has really two parts. One part has to do with standard setting. So basically with the question, what would you make the adjustment for? And at the screening stage of persistence assessment, we're mainly looking at a reference chemical approach, which means that we're trying to avoid the widespread use of chemicals with properties that closely resemble those of known POP-type compounds. And since the half-life data for POPs also mostly have been measured under laboratory conditions, it makes most sense to compare them to half-lives that have also been measured under laboratory conditions. So we really think that in this case, adjustment to environmental factors is not justified. But then there is also a confirmatory stage in persistence assessment where you start considering different risk management options and where you try, for example, to ensure that the levels of a given chemical, once it's been regulated, decrease significantly within a reasonable time frame, let's say a year. And in that case, temperature adjustment to more realistic environmental conditions may be justified. The other part of the answer to this question is where is the state of science with regard to making these adjustments? And for adjusting abiotic transformation rates to temperature or to pH, the science is really there. You can use Arrhenius equations. So if you have enough data to kind of back up how exactly you do that correction, what the activation energy, for example, is, then this is scientifically, that's okay. We don't think that the science is quite there when it comes to adjusting biotransformation rates, because we know microbial populations can adapt to certain conditions. They can have very different temperature optima, so it's very hard to predict how they will be affected by a change in temperature. So basically we think scientifically right now it is hard to adjust biotransformation rates for temperature, and that's why it shouldn't really be done. Now, an issue that is related to these environmental conditions and that Bob already kind of talked about a little bit is natural variability in half-lives. And so usually if you have different half-lives for a chemical, they're going to be a little bit all over the place. And this is maybe the most data-rich example that I could come up with. These are half-lives for atrazine degradation in soil, and these are about 470 half-lives from 55 publications that we pulled together. And you see what Bob already showed, they really range from half-lives of less than 1 day all the way up to half-lives of 600 days. So basically, our recommendation how to deal with this is simply not to use the most extreme values you can find, but to use some kind of geometric mean of the rate constants or of the half-lives. It's not proper science to use arithmetic means because that's just not mathematically not really correct in that case. As a little side note, what one can also show if you have that much data is that the data is actually not all over the place. So for example, for the 110 rates from laboratory experiments that we had, we could explain about 70% of the variance using multivariate regression by different environmental factors in the experiments, such as the pH, the organic carbon content, or the temperature. So this illustrates, again, if you have a lot of data, you might be able to derive such relationships and have a basis for correcting to environmental conditions where it's justified by the objective. And finally, a last slide on the issue of transformation products in PBT assessment. So obviously, degradation does not always mean mineralization. There are instances where a stable and/or toxic transformation product might be formed as the parent compound is transformed in the environment. Fairly well-known examples are the transformation of aldrin to dieldrin, which actually is the compound that has the PBT characteristics and the reason why aldrin itself is also regulated, or the transformation from DDT to DDE, which again is actually the more persistent compound of the two. When would you start looking for transformation products in an experiment? Well, obviously, if the disappearance time for the parent compound is much faster than the rate of mineralization. This is most easily recognized in studies with 14C labeled materials. The other interesting question is how transformation products are then dealt with in the context of POP and PBT assessment. And here the regulatory situation is such that the Stockholm POP Convention actually says that parties should be able to nominate chemicals that are not in themselves POPs, but whose transformation products satisfy the criteria established under the convention. This is contradicted at the moment by the LURTAP POP protocol that suggests that there is no basis to support the listing of a chemical solely because it has the potential to degrade to a POP-type compound. So here I think time will show how this is dealt with in practice. And with this, I would like to hand over to Gary Klečka for the question and answer session on this technical part of the seminar.
Thank you, Catherine, Jason, and Bob. Colin, I believe you said you wanted to have a brief moment while I review questions.
Yes, I just would like to remind everybody that in order to submit questions, just go up and click on the Q&A button that's in the upper left-hand corner. Remember, if you went into the full screen earlier, you can exit that by hitting Escape or F5 so you can see the Q&A button.
All right, we have some questions. We are running a bit short on time, but we do have the opportunity to take some questions here. The first question I believe is most appropriate for Catherine. Albert asks, what kind of evidence is needed to show covalent binding? Is there evidence that any chemical that cannot be extracted actually is bioavailable? If the only means to demonstrate a chemical's presence in soil or sediment is to combust to release the radioactivity, this seems to go beyond evidence for strong binding. So I think really what evidence is needed to show covalent binding?
That's a good question, and I'm really not the biggest expert in this. But basically, there are NMR techniques, for example, or also certain MSMS techniques which might help to show that covalent bonding has taken place. But perhaps some of my colleagues, Jason, do you have to add to this?
At the moment, in terms of the drugs that we test, and I know that most of the pharma industry tests, what we tend to do is a fairly exhaustive kind of extraction procedure using a range of kind of polar and non-polar solvents at different kind of pHs and ionic strengths before we actually move to some kind of soxalant-based extraction. So we try and get things off as much as possible under environmentally kind of relevant conditions, and then if we can't get them off under a range of different extraction conditions, which could be in the region of sometimes half a dozen to a dozen different kind of solvent extractions, we tend to conclude that they're not going to come off actually within kind of any conditions they face in the environment, and conclude that they're not extracted, and we use that as part of our band. But whether or not we can kind of hand on heart state they're covalently bound, we're not in that position at the moment.
I think there's quite a bit of evidence in the literature, a number of very well conducted studies that have used NMR techniques. The other thing that you tend to see sometimes if you have uniformly labeled material is that you will see a very slow evolution of carbon dioxide, and this is typically in soil or soil and sediment systems. And that is, if you calculate the rate of that carbon dioxide, you'll find that it's typically the rate at which natural humic substances turn over. So there's a fair amount of literature on this subject, and it's widely known what types of compounds are particularly prone to this. And the soil is very effective at basically humifying organic materials. If you look at the structure of humic, I think you can pick out why certain types of classes would be prone to this phenomenon. Okay, Karen asks, the REACH guidance in Chapter 7.9.5.1 states that the enhanced screening tests are restricted to using only natural environmental media as a source of inoculum, that is, marine and fresh water. enhanced screening studies using inocula derived from sewage treatment works cannot be used in persistence assessments. So that's a quote from the guidance. And she asks, what are the presenters' views on this statement?
I think I might be best to pick that up. I obviously chaired the group that drafted the technical guidance under REACH for the degradation endpoint, and actually some of the regulatory members of that working group felt that the inherent studies that we have, so things like the Zarm-Wellens and the MITI-2, were actually covering the enhanced biomass levels anyway, so they might be able to get that data via those studies, but there was also some reservation of actually using sewage treatment data for actually determining persistence once a chemical was within the wider environment. It's not necessarily because they might be different organisms and adapted organisms within a wastewater treatment plant. But that's not a view that I would necessarily hold to. I would use any evidence of biodegradation as long as the compound hasn't been pre-exposed as being some evidence of non-persistence, and then would actually look at the levels of biomass that were actually present and the rates and extent of degradation and whether or not there's any transformation products formed.
Okay, thank you. We'll have time for one or two more questions at most, but I will comment that if questions continue to come in, we will be providing responses back to those that raise the questions. So after the webinar today, if there's any remaining questions, we will certainly address those. John wants to know, is there any experimental evidence, and if so, what, that the faster rate observed in higher volume screening tests is due to increased biodiversity? Jason, that's probably a question in your section.
In terms of Nyholm's work, I think it tends to be slightly inferred in some of the work that I've yet to publish from some of my studies, where we've kind of supplemented not only the assessment of biodegradation and of the chemical, we've actually looked at the different types of bacteria, so the genetic identity and how they change from the start of the study to the end of the study, that we can see differences happening between kind of pass and fail studies, so those that show degradation, those that don't, and attribute those to differences in cell density, but also differences in cell volume as well at the outset of the study. So I would say, yes, there is a microbial reason behind that.
Okay. And then finally, Betuna asks, due to the variability, and this is in screening tests, do you think that it will be more useful to test different inoculum in screening tests than to perform only one very expensive simulation test? That would be my counsel, but Jason, how do you feel about it?
It's something I routinely do for my products now. If we're doing ready studies or we're doing enhanced biodeg studies, we screen not only a range of at least 3 different inoculum sources, we also actually look at a couple of different concentrations, and to things like the ready test, we actually supplement them with parent compound analysis as and when we can to get evidence of primary degradation and transformation product formation. So you can get more out of those simple screening studies.
Right, and the other point here, and Jason, you probably made it earlier, is that with the screening 301 tests, once you've passed, you've met the criteria.
Absolutely.
Because of the stringency of those tests and because of the lottery. So, excellent. I think at this point we will stop the questions because we're already a couple of minutes over time, and we do have a couple of case studies that I believe we'll turn it back over to Catherine and Bob, and then we'll have a final quick wrap up and perhaps any remaining questions at the end. So.
Okay, thanks, Gary. So what we're trying to do with these case studies is to reinforce or to also illustrate some of the teaching points that we tried to get across in the technical session. And we also want to reflect some of the current practices in POP and PBT assessment in the light of the CTEC-Pelston workshop outcomes. The 3 case studies we're going to look at are short-chain chlorinated paraffins, and what we're going to illustrate there is how they dealt with non-extractable residues, Then hexabromocyclododecane. There we'll look at the issues of data hierarchy in interpreting persistence and also temperature correction. And finally, FireMaster 550, where we can show the role of monitoring data in assessment and how to deal with the conflicting data. So let's move to the first case study, short-chain chlorinated paraffins, SCCPs. Their draft risk profile has actually been under consideration at the 6th meeting of the POP-ROC committee last week in Geneva. They comprise aliphatic carbon chains of 10 to 13 carbon atoms that are chlorinated in different positions and to different degrees, and usually compounds with more than 48% by weight chlorination are considered SCCPs. The summary on persistence from the draft risk profile basically states that SCCPs do meet the criterion for persistence in sediment, so they have half-lives in sediment that exceed 180 days, but that there is insufficient information to conclude on persistence in water or on persistence in soil. So what I want to do today is to look at the evidence that there is for persistence in sediment. And there is actually rather little evidence. This conclusion is based on 2 studies, and one of them was the study by Fisk and co-workers, and this was really a study on the bioaccumulation of SCCPs in earthworms, and the half-lives, the sediment half-lives that they got out of this study were somewhat of a byproduct of this bioaccumulation study. For that reason, they actually only determined sediment levels after spiking on 2 days, on day 18 and 32 after spiking of the 14C labeled C12 SCCPs, and they then analyzed the sediment in 3 ways. They did sonication with toluene, then succinate extraction with dichloromethane, and finally also direct combustion, so oxidation of the sediment to really look at the total C14 levels in the sediment. And if you look here at the table on the right-hand side, you see that the concentrations that they find with toluene extraction or succinate extraction are for both compounds quite a bit lower than the total oxidizer concentration. So basically what we are looking at here is perhaps some kind of non-extractable residue formation, about 70% that cannot be accounted for the first compound, and about 40% that cannot be accounted for the second compound. So the conclusion they draw in the paper is that it's likely that this 14C that they could not extract with toluene, but that was measured by complete combustion, are either more polar transformation products or something that is more tightly bound than the starting material. They then go on to estimate half-lives in sediment, and they say that these estimates were made by assuming that the percentage of toluene extractable 14C really represents the amount of remaining parent compound. So this is a somewhat implicit statement saying that what could not be extracted is assumed to not be parent compound anymore. So either be some kind of metabolite or some kind of non-extractable or really tightly bound material. And the half-lives they then estimated were 13 days and 30 days for the 2 different SCCPs. We discussed this study in our expert group, and basically it's obvious the half-lives that were calculated are DT50 values, so disappearance half-lives, rather than degradation half-lives. And at the same time, formation of covalent bonds was not really experimentally demonstrated, and we discussed some of the issues with that earlier. But it's also not been demonstrated for similar compounds. So it cannot be proven at this point. So for us, this means that at least the key assumption that these non-extractable residues are not available should be clearly stated for transparency reasons, and ideally really both the conservative degradation half-life and also the non-conservative disappearance half-life should be reported. It's actually interesting to note that the second sediment fate study that is available, that was carried out according to OECD 308, testing half-lives, yielded much, testing guidelines, yielded much higher half-lives in freshwater and marine sediments of over 400 days. So we think if degradation half-lives for this first study had been calculated, they would most likely be more in line with the degradation half-lives that have been found in this second study. The second case study I quickly want to talk about is hexabromocyclododecane. Again, the draft risk profile for this type of compound has been under consideration at last week's POPROC meeting in Geneva. Also, the EPA has just released an action plan on HBCD that can be downloaded from this webpage. HBCD is a mixture really of 3 different stereoisomers, and the summary on persistence from the draft risk profile concludes that HBCD does meet the criterion for persistence, and there are actually different pieces of evidence here. So the half-life in water has been found to be larger than 60 days. Measured data from sediment cores indicates slow degradation. HBCDs are also found widespread in the global environment with high levels in top predators, and there are temporally increasing concentrations of HBCDs found in biota. What I want to do now with you is look at some of the data that's available for persistence in general or persistence in sediment. And we first have some ready biodegradability data, so 301 study data, and that basically reports that HBCD is not readily biodegradable. This is also supported by BioVin calculations that also yield a non-readily biodegradability outcome. But this is then contradicted in a way by data from aerobic and anaerobic transformation studies in water sediment systems, so OECD 308 studies, which report half-lives mainly below 120 days, but certainly below 180 days. The caveat there is that they actually demonstrate that transformation products are formed, so these are not mineralization half-lives, these are just primary transformation half-lives for the parent, and this might explain some of the contradiction to the ready biodegradability studies. As a side note, it's also interesting to see that much shorter half-lives were reported for low spiked concentrations compared to the half-lives that were reported for high spiked concentrations. So that also shows some of the influence that spike concentrations might have on the outcomes of this study. But then, as mentioned before, there is also evidence in sediment cores from the 70s and the 80s that show significant amounts of SCCPs in these layers of the sediment. And the conclusion obviously was that SCCPs are persistent in sediment, and that conclusion was mainly based on the sediment core data. So obviously we have here a hierarchy of evidence, and the field monitoring data really takes precedence over the laboratory simulation studies. And it can be discussed here whether that's the way how it should be done. I think it's not obvious at this point, but one problem with sediment levels basically is that they often cannot be related back to emission levels. Basically meaning that they cannot really be used to derive actual half-lives. So it's a different kind of evidence for longevity that is given fairly high priority here, also perhaps referring back to the precautionary principle. As a side note, there are now newer studies indicating that depuration of HBCD might actually happen quite quickly in biota. So rapidly decreasing levels in porpoises after the production in the UK was ended in 2003 has been observed, and this data is now also just being submitted for publication and might influence some of these assessments in the future. A last slide on temperature correction, again for HPCD. What you see here is a table that has been taken out of the nomination dossier for this compound, so the first dossier that was compiled for this compound. And as you can see in this column here is degradation half-lives from sediment water studies are reported, and then in brackets there are also values given for half-lives corrected to 12 degrees Celsius, which obviously are higher. This temperature correction has now been taken out of the draft risk profile, which basically is consistent with the CTEC-Pelston workshop findings that the scientific basis for doing this correction with biotransformation is lacking at the moment. And with this, I would like to hand over to Bob for the last case study.
Well, hello again. I have 3 more slides on the FireMaster case study. And I'm not necessarily going to provide the answer to whether the chemical is persistent or not, but really it just highlights some persistent issues here. And so we're talking about what are inconsistent or insufficient data. Degradation products, I won't say much about that for lack of time. Does monitoring provide evidence of persistence? FireMaster 550, what is it? Well, this is a current case being handled by EPA. It's a fire retardant mixture. Has several different commercial names. It's a mixture of, as shown here by the chemical structures, 2-ethylhexyl esters of tetrabrominated benzoic acid and phthalic acids in about a 3 or 4 to 1 ratio for the two. It's used for plasticizing, flame retardant, as a plasticizing flame retardant for flexible PVC, an additive flame retardant for several types of rubber, and so forth. And there's a very brief summary here of experimental data, and there's not too much of that. It's much less than we have for SCCPs, especially, but even HBCD, which is relatively data poor actually, but has quite a bit more than these chemicals. So I've summarized it here. Less than 4% degradation in a ready biodeg test, for example. Now, a porous pot test has also been done on this mixture, as shown here in the second bullet. And porous pot is in one of the methods in the OECD 303 guideline. It's essentially a high biomass activated sludge simulation test. So lack of degradation in that test is more significant, I would say, than in the ready test. The possible degradation intermediates, or some of them anywhere, are given here. And essentially they're the hydrolysis products of the 2 main components of the mixture. Now, more importantly than all this, really, we have a shake flask die-away test shown here, down here in this bullet, which is essentially a river die-away test, a simulation test, as it were. It's not exactly the same as 308 test, but somewhat analogous in certain ways to that kind of test. It uses natural environmental water with and without suspended sediment. So here are the results that came from that test. Water, no sediment, 3.5-day half-life down here, you see, and then water with sediment, 8.5 days. Now, only one test has been done of this type. So those are pretty short half-lives, and it's pretty clear that they don't meet any of the regulatory criteria we're aware of, certainly not the 60-day half-life and water criterion. These are half-lives for the disappearance of the parent substance. In that test, degradation products weren't measured. And this is the last slide actually here, summarizing again 3.5 to 8.5 days. Clearly, from this test anyway, clearly identifies the chemicals not persistent by the standard criteria. However, weighing against that are some of the other data that are available. There's a little bit of monitoring data here. It's been found in some sewage treatment, in U.S. sewage sludge, and several measurements at one plant, and also in 2 other plants in San Francisco in 2009. Now, admittedly, that's not very much data. More important than that, I think it's been found in both of 2 marine mammal species near a flame retardant production plant in Hong Kong, and in 7 out of 7 for the first component and 5 out of 7 for the other component species in an Arctic food chain in Svalbard, Norway, in this year's study published this year. So essentially all the species in an Arctic food chain that was studied up in Svalbard. And then finally here, the TBB component has been found in polar bears at levels 30 times that of the primary prey. So now stop and think about that in conjunction with what I've set up here regarding half-lives from this aquatic die-away study, 3.5 to 8.5 days in that study. How do you reconcile those two findings? It's not exactly clear, and as I said a minute ago, I'm not going to give you the answer because I'm not sure what that answer is. What I can say is there is an action plan in EPA right now. It's in draft form, not released. Therefore, I can't talk about details, but I can make a couple of observations. First, the fact that we're still looking at it means we haven't decided that it is not persistent, therefore not of interest. We are still considering the chemical. Some of the actions that are being considered now are to put it on an EPA risk list, and also, more important perhaps, to consider developing a test rule which is the purpose of which under the Toxics Control Act is to develop more data to try to get a better handle on the risks from these chemicals. So that's all I have to say.
All right. I want to thank everybody for their patience and their attendance this morning. We have one remaining question that I'll pose to the presenters, although Bob is probably best directed at you, and that is, can the presenters comment on the importance of risk assessment in the PBT assessment? For example, what if a compound is persistent in a compartment or found in a compartment but has no toxicity in that compartment?
Well, you know, are you referring to the, for example, the Stockholm Convention, the context of the International POPs conventions and so forth?
I don't know that the question is stated that specifically. It's more general in terms of PBT assessment. And so it's going to likely the answer is going to vary depending upon what convention or regulation you're talking to.
And I think the answer varies with the context as well. Certainly, for example, when we're in the context of new chemical assessment, pre-manufacture notice assessment under TSCA, where risk is an extremely important part of the equation. We consider PBT properties, but risk is also an important part of that. I think the question is probably best directed at people in our risk assessment division, and Tala Henry, for example.
Okay. Thank you for the response. That being the end of the questions, and if there are any remaining ones that I'm looking at that are kind of specific, we will certainly get responses back to those that posed the question. So with that, I believe we can conclude the webinar this morning. Colin, I'll turn it back over to you.
Thank you very much, Gary. At this time, a survey is coming up on your screen. The screen is now under your control. We would appreciate if you take a few moments before you log off to give us your feedback. We really appreciate that. Also, remember, you will be receiving an email probably later tomorrow that will give you access to allow you to view and or download a recording of today's event and the handouts. You will have 2 weeks to to make use of that, so please make sure you do. After that time, the link will be disabled, so please jump on that as soon as you receive it. On behalf of CTAC, I want to thank you all for attending today and for your great questions. We also want to thank all of our speakers, and we look forward to seeing you again at an upcoming event. Thank you, everybody. That does conclude today's event. Have a nice day.